Welcome to The Explainer. Today, we're diving into a mathematical mystery that has literally been bugging AI developers for years. We're talking about the true mechanics behind AI model compression. We're going to explore a brand new preprint, arXiv 2607.08776v1, that finally brings a unified theoretical framework to the table. If you build, fine-tune, or deploy large language models, you already know how critical efficiency is. So today's explainer is going to show you exactly how the science of compression is evolving.
Which brings us to the ultimate question, right? Why does knowledge distillation actually work? As developers, we rely on KD as the absolute industry standard for getting massive LLMs into production. You take a giant, highly capable teacher model and use it to train a smaller, faster student model. We know the student gets better, but why it works has honestly been a black box. We just ran the training loop, crossed our fingers, and hoped for the best. Well, until now.
Okay, let's just jump right into the agenda. First, we'll look at the knowledge distillation mystery, then unlock interactions and sparsification. Next, we'll introduce the complex interaction penalty, evaluate the performance gains and trade-offs, and wrap up with next steps for developers.
So, starting with Section 1, the knowledge distillation mystery, finding the common denominator.
What's absolutely wild here is this massive shift in our fundamental understanding of distillation. For the longest time, the old assumption in the AI community was that distillation was all about replicating the teacher's behavior verbatim. We basically thought the student was just trying its hardest to perfectly mimic the teacher's logics or hidden states. But the new reality, the thing this research proves, is completely different. The student isn't just a copycat, it's an editor. Real successful distillation is actually about preserving the core predictive signal while intentionally pruning away the super complex, highly specific dependencies the teacher uses. And here's the kicker. Different KD methods, whether you're using logic matching, intermediate layer alignment, or whatever, all share this exact same unexplained common denominator. They work because they edit out the noise.
Moving to Section 2. Unlocking interactions and sparsification. This is really the aha moment of the paper. To really grasp this breakthrough, we have to look at how these researchers modeled LLM outputs. They treated the output as a compositional function of input interactions. So what exactly is an interaction? Basically, it's a nonlinear relationship involving a set of input variables, like your tokens or words, that combine to produce an LLM's output score. Because think about it. When an LLM processes a sequence, it's not evaluating tokens in perfect isolation. The final output score emerges from these nonlinear dependencies between token pairs, triples, and even longer subsequences. The researchers actually managed to decompose the output to isolate these specific dependencies.
And this leads us to the core revelation. I want to read this quote directly from the arXiv abstract because it's that important. Student models retain fewer interactions for inference while suppressing other interactions to zero effects. That right there is the secret mechanism behind knowledge distillation, sparsification. Student models don't succeed by learning everything the teacher knows. They succeed by selectively keeping a tiny, useful subset of interactions and completely zeroing out the rest.
The best way to picture this is with a pruning analogy. Imagine a massive, overgrown tree. That's your teacher model. It has thick branches of core knowledge, sure, but it also has thousands of tiny, tangled twigs. Those twigs represent highly complex, high-order interactions specific to its gigantic training data. During successful distillation, the student inherently prunes that tree. It just chops off those high-order, noisy twigs that the teacher relied on, but which are completely unnecessary for the actual target task. It proves that successful student models aren't sponges. They're ruthless editors. This sparsification is exactly what allows the student to converge faster, reduce compute overhead during inference, and crucially, avoid overfitting to the teacher's weird artifacts.
All right, Section 3, the complex interaction penalty. Let's talk about enforcing that sparsity. If sparsification is the secret sauce, how do we actually guarantee it happens? Well, the paper introduces a brilliant new tool called the complex interaction penalty, or CIP. It's a modular, plug-and-play loss function designed to make interaction sparsification explicit. You're not just crossing your fingers and hoping it emerges naturally anymore. By integrating CIP, you are shifting knowledge distillation completely away from endless heuristic tuning and moving it firmly into the realm of structured regularization. And this brilliantly illustrates how easy it is to drop into your workflow. The real beauty of CIP is its architecture-agnostic design. You don't have to rip apart your underlying attention mechanisms or modify model layers to use it. It works by first calculating the magnitude of high-order interactions in the student's hidden states or logits. Then, it slaps a penalty on them proportional to how much the student tries to retain them. Plus, it scales with interaction complexity, so those lower-order dependencies carrying the actual task-specific signal are left completely untouched, while the high-order noise gets heavily penalized. You literally just let it accumulate in your training loop right alongside your standard KD losses, like KL divergence or MSE.
Which brings us to Section 4, Performance Gains and Trade-offs. Let's balance the hype a bit.
Let's ground this complex math in developer reality and look at the actual impacts. For generalization, integrating CIP yields consistent, pronounced gains on out-of-distribution, or OOD benchmarks. And for overfitting, because explicit sparsification stops the student from simply memorizing teacher-specific patterns that failed to generalize, it massively mitigates the issue. But we do have to talk about compute overhead. Decomposing these interactions requires tracking token-level dependencies during forward passes, and that undeniably adds memory and compute pressure to your gradients.
So, how do we manage that compute cost? The magic number you need to remember here is 3. The researchers note that while decomposing interactions definitely adds overhead, you can approximate the penalty using sampled subsets. For practical implementation, unless you're running on absolute bleeding-edge hardware with unlimited memory, you should limit your interaction tracking order to the second or at maximum the third degree. Doing that keeps your training costs entirely manageable while still capturing the vast majority of the sparsification benefits.
Finally, Section 5, Next Steps for Developers. Let's look at the playbook.
Let's move to a pragmatic guide you can use today. Step 1, audit your current KD pipeline to find where your performance plateaus, especially on OD data. 2, integrate CIP as a modular loss. 3, validate on distribution shifts. Run your evaluations on held-out domains or prompt variations, because this is where CIP really shines, when the student hits inputs outside the teacher's training data. 4, make sure to profile your computational overhead carefully. And 5, avoid blind adoption. We'll touch more on that last point in a second. But before we do, here is a highly specific pro tip for your integration. Do not blast this penalty at full strength right out of the gate. Start with a very low coefficient, around 0.01 to 0.05. You want to schedule this to slowly increase as the distillation process progresses. Treat it as a gentle regularization layer that just nudges the student toward efficient representations over time. And returning to that avoid blind adoption point, you need to know when to pause on CIP. The whole concept assumes that sparsification improves generalization, which for most natural language tasks, it absolutely does. However, if your model is working on tasks that require fine-grained token-level reasoning, like code generation, or tasks with really strict formatting constraints, excessive sparsification might actually discard the complex dependencies you need to get the syntax right. Always test incrementally, and if your validation metrics drop on these specific tasks, just dial the penalty back.
All right, so we've covered a massive paradigm shift today. By proving that sparsification is the real engine of model compression, this research gives us a tangible tool to build smarter, not just smaller models. Which leaves us with a final question to ponder. Is the future of LLM efficiency entirely about structured regularization, finally moving us away from the dark arts of heuristic tuning? I highly encourage you to check out the full methodology and mathematical derivations in the arXiv paper to see for yourself. Thanks for joining me on The Explainer, and keep building.